So this is part 3 of the video series on chair conformations. In this video, we're going to go through how to do a chair flip once we already have our initial chair structure. So in the previous section, or part 2 of this video series, we drew out this structure here on the left. And so now we're going to go through how do we draw the second structure that corresponds to this chair. And so in our step 1, we're going to draw that initial chair structure, which we already did. And then we're going to draw the empty chair that corresponds to the other structure. And so for this, I'm going to copy the structure from up here. And again, the main thing that we're paying attention to for when we're choosing which empty structure that we draw is that we want to make sure that these outside parallel lines are in the opposite directions as the ones on the left. So we can see that the structure on the left, they're tilted to the right. The structure on the right, they're tilted to the left. All right. Next, what we're going to do in step 2 is we have that each carbon shifts over one spot going clockwise. So in that previous video, we assigned this top right as carbon number 1. So once we do that chair flip, we're going to move over one spot clockwise. So now our carbon 1 is going to be here. And so since our substituents shifted over, we will also have to fill in those that correspond to each of the carbons that had substituents in that initial structure. All right, so I drew in those empty bonds that correspond to those substituents. Next, we're going to fill in for step 3, each of the substituents. And what we know is that each substituent flips from its axial equatorial positioning to the opposite. So if it was axial, then it will be equatorial. And if it was equatorial, it will become axial. Okay, so what does that mean? So for this next step, what we're going to do is label all of these substituents as either axial or equatorial. And again, for this, we're looking at anything that's pointed directly up or down, like those ones in the blue. Those are going to be axial. And I'm just going to put axial in parentheses next to them. And then anything that's pointed to the side, so a little bit more like parallel with the page, all of those are going to be equatorial. And so if we look at carbon 1, we initially had a chlorine and hydrogen A on there. And so if chlorine was initially axial, that means that once we shift over to that second position, there it's going to be equatorial. And so the equatorial position is the one that points side to side. And that also means that the HA, which was initially equatorial, will flip and become axial. And then we can also do the same thing with HB and bromine. So that bromine was initially axial, so then it'll become equatorial here, and HB will be that axial position pointed up. Same thing with the OH and the HC. That OH was initially equatorial, so it'll become axial, and then HC will be equatorial. And so now what we can see is those 3 highlighted in purple groups are now equatorial. And the ones highlighted in green are the axial ones. You can see that they're pointed up and down now. And this kind of makes sense with like the wedge and dash discussion that we had in the previous video, where all of these groups still tilt the same way. So for example, that OH, in that first structure, it's tilted slightly up. And in the second structure, it's also tilted up, even though it switched from being equatorial to axial in those structures. Similarly, we can take a look at something like HA. So HA in that first structure is highlighted in purple and is tilted slightly down. And then in the structure on the right over here, it's completely pointed down. And so it's switching from equatorial to axial, but still retaining that tilt that indicates that it's going to be a dashed representation within the skeletal notation. All right, that's really it. In the next video, we'll talk about how to determine which structure is more stable at equilibrium based off of the axial and equatorial positioning of each of the substituents.